In this video, we'll explore the fundamental concepts of computer networking. Whether you're a beginner or just looking to refresh your knowledge, this guide will help you understand how networks connect devices, share information, and keep our digital world running smoothly. We'll cover essential topics like network types, topologies, devices, protocols, IP addressing, the OSI model, network security, and basic troubleshooting. By the end of this video, you'll have a solid foundation in IT networking and be ready to dive deeper into this fascinating field. So let's get started and unravel the mysteries of IT networks together. Let's explore the fascinating types of networks that keep us connected, from the tiny personal area network, or PAN, around you, to the local area network, or LAN, in your home or office, the campus area network, or CAN, in schools, the metropolitan area network, or MAN, spanning cities, and the vast, wide area network, WAN, that covers the globe. We'll dive in and see how these networks make our digital world go round. A personal area network, or PAN, is the simplest type of computer network, designed to connect devices within a short range, typically around a single individual. It enables your personal devices such as smartphones, tablets, laptops, and wearables to communicate and share data with each other. PANs have a range up to 33 feet, offering high transmission speeds, easy maintenance, and low costs. Examples of devices that can be part of a PAN are laptops, smartphones, tablets, printers, and keyboards. A local area network, or LAN, is a network that connects devices within a limited area, such as a home, office, or building. LANs are typically used to share resources like files, printers, and internet connections among multiple devices. They are essential for enabling communication and collaboration within a localized environment. A campus area network, or CAN, is larger than a LAN but smaller than a MAN, which we'll talk about next. Typically used in environments like schools or colleges, this type of network spans a limited geographical area, covering several buildings within a campus. CANs primarily use Ethernet technology and have a range of around 3 miles. They offer high transmission speeds with moderate maintenance and overall costs. Examples of CANs include networks that cover schools, colleges, and other campus buildings. A metropolitan area network, or MAN, is larger than a LAN but smaller than a WAN. Designed to connect computers over a geographical distance within a city, town, or metropolitan area, MANs offer average transmission speeds, are challenging to maintain, and come with high maintenance costs. Examples of MANs include networks that cover towns, cities, or large areas within multiple buildings. A wide area network, or WAN, spans a large geographical area, often connecting multiple LANs across cities, countries, or even continents. WANs are used by organizations to facilitate communication and data exchange between distant locations. The Internet is the largest example of a WAN, providing global connectivity and access to information. A network topology is the physical and logical arrangement of nodes and connections in a network. Nodes usually include devices such as switches, routers, and software with switch and router features. Common topologies include bus, where all devices share a single communication line; star, where all devices connect to a central hub; ring, where each device connects to 2 others forming a circular pathway; mesh, where devices are interconnected with many redundant connections; and tree, which combines characteristics of star and bus topologies. Each topology has its own advantages and disadvantages, influencing factors like performance, scalability, and fault tolerance. Network devices are essential components that facilitate communication and data exchange within a network. Here are a few that you may see out in the wild. Key devices include routers, which direct data packets between networks, switches, which connect devices and send data frames within a single network, and modems, which convert digital data to analog signals and vice versa for internet connectivity. Additionally, firewalls protect networks from unauthorized access and cyber threats. A network protocol is a set of established rules that dictate how data is transmitted between devices. These protocols enable connected devices to communicate seamlessly, regardless of their internal processes, structure, or design. Thanks to network protocols, you can easily connect with people worldwide, making them essential for modern digital communications. Just as speaking the same language simplifies communication between people, network protocols allow devices to interact by following predefined rules embedded in their software and hardware. Without network protocols, neither local area networks nor wide area networks would function as they do today. There are thousands of network protocols. We're just scratching the surface here. IP addressing is a fundamental aspect of networking that involves assigning unique identifiers to devices on a network. There are two main types of IP addresses: IPv4, which uses a 32-bit address format, and IPv6, which uses a 128-bit address format to accommodate the growing number of internet-connected devices. IP addresses enable devices to locate and communicate with each other over a network. The subnet mask is the number that distinguishes the network address and the host address. A subnet mask of 255.255.255.0 indicates that the network address will consist of the first three IP address octets, and the fourth octet will be reserved for the host address. Subnetting is a technique used to divide a larger network into smaller, more manageable subnetworks, improving efficiency and security. Understanding IP addressing is crucial for network configuration and management. This quick explanation of IP addressing barely scratches the surface, so please refer to one of the many resources available on the World Wide Web for additional information. The OSI model is a conceptual framework used to understand and standardize the functions of a networking system. It divides the communication process into 7 distinct layers. To transfer human-readable information over a network from one device to another, the data must traverse down these layers of the OSI model on the sending device, then move up the 7 layers on the receiving device. From the bottom to the top, the layers are physical, data link, network, transport, session, presentation, and application. Each layer has specific responsibilities, from the physical transmission of data to the application-level interactions. This model helps network professionals troubleshoot issues, design efficient networks, and ensure interoperability between different networking technologies and protocols. Let's take a closer look at the 7 layers of the OSI model. At the base of the OSI model is the physical layer, which represents the system's electrical and physical aspects. This includes everything from cable types and radio frequency links, like in a Wi-Fi network, to the layout of pins, voltages, and other physical requirements. When networking issues arise, many professionals first check the physical layer to ensure all cables are properly connected and that power plugs haven't been disconnected from routers, switches, or computers. The data link layer facilitates node-to-node data transfer between directly connected nodes and manages error correction from the physical layer. It consists of 2 sublayers, the media access control layer and the logical link control layer. In networking, most switches operate at layer 2. However, some switches also function at layer 3 to support virtual LANs that span multiple switch subnets, requiring routing capabilities. The network layer is where most of the router functionality is found. Essentially, this layer handles packet forwarding, including routing through various routers. For instance, if your computer in Detroit needs to connect to a server in Washington, there are millions of possible paths. Routers at this layer ensure this process is done efficiently. The transport layer manages the coordination of data transfer between end systems and hosts. determining how much data to send, at what rate, and where it should go. The most well-known example of the transport layer is the Transmission Control Protocol, or TCP, which operates at the top of the Internet Protocol, or IP, collectively known as TCP/IP. TCP and UDP port numbers function at Layer 4, while IP addresses operate at Layer 3, the network layer. When two computers or network devices need to communicate, a session is established at the session layer. This layer handles the setup, coordination, such as determining how long a system should wait for a response, and termination of the session between applications at each end. The presentation layer is responsible for the translation or preparation of data between the application format and the network format. Essentially, it presents data for the application or the network. A common example of this is the encryption and decryption of data for secure transmission, which occurs at Layer 6. The application layer is the layer that's closest to the end user. It directly receives information from users and displays incoming data to them. Interestingly, applications themselves do not reside at this layer. Instead, the application layer facilitates communication through the lower layers to establish connections with applications at the other end. Examples of communications that rely on Layer 7 include web browsers, SSH, and FTP. Network security is crucial for protecting data and resources from unauthorized access, cyber threats, and attacks. It involves implementing measures such as firewalls, encryption, antivirus software, and intrusion prevention and detection systems to safeguard network integrity and confidentiality. Common threats include malware, phishing, and denial of service attacks. By employing robust security practices, organizations can ensure the safety of their networks, maintain user privacy, and prevent data breaches. Basic troubleshooting involves identifying and resolving common network issues to ensure smooth operation. Key steps include checking physical connections, verifying IP configurations, and using tools like ping and traceroute to diagnose connectivity problems. Understanding how to reset network devices, update firmware, and address common errors like IP conflicts or slow network speeds can help maintain a reliable and efficient network. Effective troubleshooting skills are essential for quickly resolving issues and minimizing downtime. Here are the 6 troubleshooting steps recommended by CompTIA, the Computing Technology Industry Association. Identify the problem. It's crucial to understand that the underlying cause of certain problems isn't always obvious. For instance, a failed login attempt might initially suggest an incorrect username or password. However, the actual issue could be a lack of network connectivity, which prevents the authentication details from being verified by a remote server. Establish a theory of probable cause. This phase might demand extensive research on your end. You may need to consult vendor documentation, your organization's internal resources, or even perform a thorough Google search to support your hypothesis. It's essentially a process of elimination. Many device manufacturers offer documentation, issue repositories, and forums where troubleshooters can share ideas and learn about common issues, solutions, and troubleshooting techniques from other IT professionals. Test the theory to determine the cause. With the tools at your disposal, it's time to test your hypothesis. If you suspect the network router is faulty, try replacing it with another router to see if that resolves the issue. It's crucial to remember that disproving your own theories doesn't equate to failure. Instead, it signifies that it's time to revisit Step 2, formulate a new hypothesis, and find a way to test it. While your initial theory might sometimes be correct, it's also common to cycle through several hypotheses before pinpointing the true cause of your network issues. Establish a plan of action to resolve the problem and identify potential effects. Once you've validated your theory about the network issues, you're ready to address them. Develop a plan of action to tackle the problem. Sometimes, your plan might involve a single step like restarting the router. In other instances, it could be more intricate and time-consuming, such as ordering a new part or rolling back software to a previous version on multiple users' computers. Verify full system functionality and, if applicable, implement preventative measures. After implementing your solution, it's essential to test the network. Ensure that the original issue has been resolved, but also watch for any new problems that might have emerged from the changes you made. As part of your verification process, use the network tools available to you and gather feedback from individual users about their experiences on the network. Document findings, actions, outcomes, and lessons learned. If you're a network professional or enthusiast frequently dealing with networks, it's likely you will encounter this issue again. Be sure to document each stage of the troubleshooting process, including the symptoms observed, the theory you developed, your testing strategy, and the solution you implemented. Even if you don't refer to this documentation later, it would be invaluable to a coworker in the future and help reduce network downtime. Thanks for watching. If you found this video helpful, head on over to our channel for more great technical tutorials. And come on down to our forum. It's a great resource for everything WinTech.